All right, line A4, learning task 11. We're going to take a look at solving power factor correction problems. You should notice that there is a little bit of a pattern here. Once we get through the theory and get to the problems, they're usually fairly long sets of videos because there's a lot of problems to go through and to go and solve. This one's going to be no different. It's got a lot of triangles. If you go back through the learning task 11, you should see all those triangles. You should also note that all those triangles, though, at this point are watts, or at least I think they all are. I don't know. Just glance through them right now, but I'm pretty certain we've only got power triangles that are going to be inside of there. And you'll note as well that all of my power triangles at this point are going to be following what we refer to as convention. The convention for power triangles is if it is going to be a vars L type of triangle, I'm going to go and draw that triangle to the top, like that. And if it's going to be a vars C triangle, I would go and draw that triangle down to the bottom. So, that would be my vars C. Direction is not going to go and be important to us, as long as we go and make sure that wherever we draw our vars L, we draw our vars C in opposition to them, so that we can get to the next of whatever we're going to have. We're also going to go and use the terms leading and lagging. If I've got a vectors that's going to go and look like this, I would say that whatever my VA is going to be would be leading. Why is it leading? Because it is vars C that I'm going to see inside of here. If I've got a VA up here, I'm going to go and call this thing VA lagging, that I'm going to go and have for that circuit, because it's got vars L. It's got a primarily inductive types of vars. Power factor would be done the same way. This is going to go and have a lagging power factor based on the phase angle. This would go and have a leading power factor based on the phase angle there. There's also a number of example triangles that they give you inside there that just kind of show how we should be able to go and recognize something that's going to have a good power factor compared to something that's going to have a poor power factor. We know that power factor is simply going to go and be my measurement of my watts over top of my VA. Hypotenuse is always going to be the VA, so if I'm looking at watts, which are always on the X over top of my VA, I see it would only be a small percentage. Therefore, this thing would have a poor power factor and a large phase angle. This one over here, I see I got a large amount of watts compared to my VA. Therefore, I'm going to go and have a relatively small phase angle and what we would refer to as a good power factor. The book also goes over how we can go and correct, right? Where we can go and take any sort of a power factor, whatever we have, that's going to be made up of my watts and my vars, and then I can go and take and I can collapse that hypotenuse back in onto the watts itself. How do I do that? Well, I would do that by taking out the vars. The way that we take out vars is we just add in vars of the opposite type. Remember that nature tends to want to go in balance, that we are going to go and have inductance and capacitance that are going to be seen in opposition to each other and able to cancel each other's effects. So we're going to go through a bunch of cases and examples. The cases are not examples. The cases are just where they're saying, look, there's two ways that we are going to go about that. First of all, case A is going to be where I'm given a power factor and one other info. That's it. That's going to be my case A. And then I'm going to have to go and convert. Well, since we're given a power factor, we are given a phase angle. And as soon as we are given a phase angle, we can go and punch that thing into our calculator really, really quickly. They say that, you know, look, if we're given a VA, and it's right underneath the case A over there, if we're given something where we're told that this thing is going to be 300 kVA, and if we're given a power factor of 70% lagging, so 70% lagging power factor that I'm going to have, we can calculate everything else from there. Really simple for us to go and do so. Change this into an angle. Take that 300 kVA, put it at the angle. How do I change a power factor into an angle? Well, we're just going to punch into the calculator using our cosine function. Here's my calculator. We're looking, we got a 70% power factor. We're going to go and take the inverse cosine of 0.7, which is our power factor, which spits out an angle of 45.57 degrees. They round that up to 45.6 inside of your binder, but that's the exact same thing. That's figure 5 inside of your binder. Now, here's where this thing gets beautiful. I did this all as a step. What I can also do is I can put this all in as a complete formula. I can put in my VA at my angle, which is going to be my, and then use a bracket, cos to the -1 of my power factor, bracket, bracket. And that will go and spit out the entire thing without me having to write down an angle or anything like that. Let's go and do that on our calculators over here. We're going to go and use the inverse cosine of our power factor with the VA. First of all, I'm going to make sure I'm in the proper mode. So I've got to be in mode 3. I'm in XY right now. We're just going to put that thing into polar mode. I could have left it in XY. We're going to convert back anyways. But now I'm just going to punch this in. 300 angle of, and I'm just going to go and punch this in as a bracket because this is what my angle is. Second cosine of 0.7. Close off your brackets like that and hit equals. Punches out, gives us cosine, and what it does is it gives us the angular degrees when I comma over. So it tells me the angular degrees. Even better yet, I do that conversion to my XY, and it tells me immediately that I've got an X value, therefore watts, of 210. So this is kilowatts. This would also have to be kilowatts, 210 kilowatts. And that I've got a Y value of 214.24 kilovars that I'm going to go and have for it. Lovely, super fast. Okay, it's going to be, let us get to what we need to understand, the power factor correction, relatively quickly. The next example that they gave you was where they went and took two values. They said, look, we've got a load that's got 750 kVA and 400 kilowatts, and I want to know what I have for my actual, power factor. This one over here, we can go and do the same thing if we really want, or we can go into Pythagoras. They go through into Pythagoras to go and do so. So draw these ones out over here. It's 750. And then this is 400 watts. This is my, that's kilowatts. This is going to be my kVA over here. They go into Pythagoras, solve for that third side, and then from that third side, then they go back using, cosine or tangent or inverse cosine. I can't remember. They use the inverse cosine to go and solve back to that. What I'm recognizing over here, though, is that I've got watts over top of VA, which is equal to my power factor. So that equals my power factor. I can once again punch this thing in all as one thing. It just this one over here to get to the same values. All I would have to do is put in my VA, so 750 at an angle of, and then it's going to bracket the inverse cosine of the power factor, which is, I don't even know what it is, but I don't really care that much because I'm just going to go and do my 400 divided by 750, my watts, over top of my VA like that. Once again, just punch it in with a number of brackets like that. As we do that, we're just putting in our VA at our angle. The inverse cosine of our power factor is always going to be our angle. 750, why don't I just put it back into polar there. 750 at an angle of bracket, inverse cosine of bracket. Now I'm going to put my watts, 100, divided by my VA, 750, brackets, close off the brackets, hit enter. Punches this thing out, and we can find our phase angle, 57.7 degrees. That it's going to give us. And immediately, we just do that XY conversion, which gives me my x-axis of 400. We already had that value, and gives me my y value of 634.4. Excellent. Once we have those ones in there, we have got the all-important VARs value. And that's really what we're going to be looking for in a lot of these cases is we need the VARs so that we can calculate out how to do the power factor correction. We're going to start by doing unity power factor correction, and then after that we're going to go into partial power factor correction, which is what we do in the fields. So we'll explore the concept first, then we're going to go and make it practical. I'm not going to go and use all of the triangles that are inside of the binder, because we're just going to be drawing these as we go along. It doesn't make much sense to go and have all of those and have to click through those slides. So you just got to follow along inside of your binder. Start with example number 1. You're told that the uncorrected power factor of a load is 40% lagging. So 40% PF lagging. And that the kilowatts is 250 kilowatts. Okay, that's our two values that we have over here. And what we need to now do is we need to go and convert that power factor into unity. In other words, we need to go and take out all of the capacitive vars that we are going to go and do. So we need to just find capacitive vars. That's all that we're trying to do. They're not asking us for line current or for anything like that. Here's what we're going to do. We know our power factor. Power factor is equal to my watts over top of my VA. If I cross multiply that back down, take the PF down, take the VA up, what I'll end up with is my VA is equal to my watts divided by my power factor. So I'm going to do that. I'm going to create the VA, and then we're just going to punch it into our calculators once again. So 250 divided by 0.4. Which is going to give us a value of 625. So that now becomes my new VA, 625. I don't know what angle it is. I can do the inverse cosine of my power factor to go and find that angle, or I can just punch it all in as one shot. That's what we're going to go and do. So we're going to go and put ourselves back into this polar mode here. I'm going to go 625 at an angle of bracket inverse cosine 0.4. Inverse cosine of the power factor is always going to be my angle. So it's 625 at its angle. I hit enter. Tells me that the angle for this thing is going to go and be 66.42 degrees. And then if I go back into it and I do that conversion to my XY, tells me my X value of 250 kilowatts. We already have that, but more importantly, it tells me my Y value that I'm going to have over here of 572.8. K bars. This would be the size of capacitance that I would need to go and place in there, or capacitive power, my quadrature, my bars that I need to go and cancel that. This is not a capacitor size in farads or anything like that. This is just my capacitive power itself. It's a really simple one because we're taking out all of my vars out of this thing. If I were to go and look at the circuitry, whatever this thing was, we can go and say that maybe this thing was a motor over here because it's got a bunch of bars and it's got some resistance inside of it. All I would be doing is placing this large capacitance right across it, and that would go and take that thing out. Is there a danger in this? Absolutely, there is a danger in this. And the danger in doing this type of power factor correction would be that if I put in this amount of vars C, so I've got this vars L, and I then match it with a vars C, and then if something happens to this load, either my vars L decrease, it gets more efficient somehow, or my watts, the amount of true power, decreases, it's going to go and change what I have. And I'm going to have too many vars C at that point, which means that I'm going to go into a leading power factor, an overcorrected power factor. Overcorrected power factors are always going to be bad. They're going to lead to an increased terminal value of voltage on a transformer. So we just want to try and avoid that. We'll examine some stuff for that later on. Let's go and take a look at example number 2. They give us another one here where we are going to now have two values for it. So I'm just going to erase all of this here. They give us a load that draws 250 kVA, 250 kVA, and has 150 kilowatts. Okay, you should notice that there's a pattern over here where they're giving us kVA and kilowatts, because normally in the field that's what we're going to get. We've got watt meters, which measure true, pure power, and we've got VA that we can get by sticking an ammeter around the line and sticking a voltmeter across the line and multiplying those two values together. What we don't have is a barometer. It's something that's going to go and measure our vars. All of our vars, even on power quality meters, are always a calculated value based off of the difference between my watts and between my VA that we are going to have. We're going to calculate this one for what we would need to get to unity off of here. Two ways that we can go about calculating that. If we're just looking for the unity power factor, if we don't, or the unity correction, we're not really concerned about the power factor or anything like that, we could do that just by Pythagoras. Take a root 250 squared minus 150 squared. And when we do that, it's going to punch out 200. Do I care what this degrees is or what my power factor is? No, because they're telling us that we are going to go and correct it to unity, which just basically means find the missing side of the triangle and then nuke it. Take the whole thing right out of here. If I would do so, I would drop my total kVA for my circuit down to that 150 kilowatts. That would be a very handy thing for us because then we would have a reduced line current, right? If I take a look at this, 250 kVA, and I'm dropping that down to 150 kilowatt, I'm almost having my value of line current inside of it. Okay, the next thing that they're going to go and ask us is a little bit more complex, where we're going to start going into values of currents as well. And they're giving us a system that we have got a load. We don't know what that load is, but they're telling us we have got 240 volts that we're giving. We're told that we have got real power, true power of this load that is going to go and be 8.5 kilowatts off of here. And I'm told that the current is going to go and be 65 amps. So 240 volts, 65 amps. I'm going to put that right here at the source because it's coming from our source as well. We are to go and correct this thing to unity. Well, if I take a look, I see I've got volts and amps at my source. My line voltage, line current together is going to go and give me my VA. So we're going to go and multiply those two together. 240 times 65, which gets me to a value of 15,600. So 15.6 kVA that I'm going to go and have. I have now got kVA and I have got kilowatts. What I can do is I can go and develop a triangle off of that, right? We've got 8.5 and we have got 15.6. I can do my watts over top of VA, which is going to go get me my power factor. Let's go and do that. 8.5 divided by 15.6 equals a value of 54%, or 0.5444. And if I take the inverse cosine of that, we'll first just write that one down, 54% power factor. If I take the inverse cosine of that power factor, gets me out to a degrees off of this one. That is going to be 56.98 degrees. Lovely. 56.98 degrees. Once we've got this degrees, we can go and solve out for our k-bars off of that thing. We just punch that all into our calculator, let that thing solve for us. When it does solve for us, we will then be able to go and figure out, our bar sign. Alternatively, you can use 15.6 and 8.5 over here to go and figure out what you have, for this side over here. Let's do that with Pythagoras off of this one. We've done a lot of the other method, so we might as well do this one. 15.6 squared by VA squared minus my watts, 8.5 squared. And I take the square root of that whole thing. When I do so, I'm going to go and kick out to get a value of 13.1 k-bars. Lovely. We'll get rid of that there. Now that we've got that k-bars, we know what size of capacitor, right? Because we've got this circuit inside of here. That's a motor. It's an inductive. We knew it was inductive because they said that they wanted to know what the capacitor would be. So we know the size of our cap that we're going to go and place onto there. We're going to add in a cap that is going to be 13.1 kVAR. Okay, now let's get to the last things that they ask us about inside of here. They want to know a bunch of currents that we are going to go and have. Initially, we had 65 amps. As soon as we add that cap on over there, we're going to go and take out that 65 amps. Because now we're going to start feeding some of those amps from this side, which means we're also going to go and take out that 15.6 kVA. This load over here is still going to be 15.6 kVA. But what my source is supplying is now going to have dropped because we're not all supplying it from the source. Some comes from the cap itself. How much do we supply from the source? Well, from the source, we're now only going to be supplying the watts they're going to be coming in from here. And all of my VARs are going to be coming in from here. So we can figure out now what we have got for current. Well, what are we supplying it here? We're only supplying the watts of 8.5 kilowatts. We got 240 volts. We know that power is equal to my E that I've got, E squared over top of R, or that my power is equal to my I squared times R. I know my value of voltage. I don't know any of my values of resistance, impedance, or anything like that. I do have one further one that is probably our most useful one. I times V. My current times my volts is always going to go give me a form of power. Do I have that for each of these? I've got power and I've got volts for all of these because it's a parallel circuit. So that's the formula that we're going to go and select. Remove these ones because we don't need them. And then we're just going to go and take our values of power and we're going to divide out our values of voltage. I is equal to my power divided by my voltage. Let's go to this one over here. What is my type of power that I'm supplying from the source? I'm only supplying the watts of 8.5 kilowatts. So 8,500 divided by 240 gets me to a value of 35.4 amps. My new line current is going to be 35.4 amps over there. Then we're going to go and take a look at this cap. This cap is going to be supplying only VARs that we are going to go and have. I wrote KVA there. That's kVARs. Let's just fix that. That's supplying my kVARs. So we're going to do the same thing. 13,100. That's too many there. We will delete one. 13,100 divided by 240 gets me to a value of 54.6. 54.6 amps. If I take this 54.6 amps and I feed that in here, and I take this 35.4 amps and I feed that in here, what am I going to get through here? We'll quickly put it into the calculator. We know this is going to be at 0 degrees. We know this is going to be at 90 degrees. So we'll go 35.4 angle 0 plus 54.6 at an angle of 90. Which gets me to a value of 65 amps. Where have we seen that 65 amps before? That was our original source current. We are still supplying the same original source load that we had over there, 65 amp load. It was a 15.6 kVA load. We're still going to supply that same 15.6 kVA over here off of this, but now we're just supplying it partially from the cap and partially from the load itself. It's a wonderful, cool thing. We see that our line current has dropped significantly. This is a big deal to us. Example number 4 gives us a couple of values as well. We're going to go and finish up these full power factor correction, then we'll go start a new video for the partial power factor correction. But example number 4 over here says refer to a figure 12. It's a backwards case that they're doing. They're told that we need to have 500 kVARs of capacitance to go and fix something up. So here's a supply. Here's a load. Like that. And then what we are doing is we are adding in capacitance to go and fix it. 500, that's 50, 500 kVARs. Okay, so we had to add in 500 kVARs to correct unity. Before correction, the original kVA was 750. So originally, we'll put that up over there. It was at one time 750 kVA. And it was fed from a 600 volt line. What was my original power factor? All that they're asking us about over here is, what we originally had off there. At this point, if we're corrected to unity, we know that our power factor is going to be 100%, but originally we had this triangle with the 750 kVA, and then the 500 kVARs that we would have over here. Do we need to go and figure out what our original current was? Not really. We could go and take a look. Oh, actually it says we are still to determine what the line current is before and after correction, as well as the current drawn by the capacitors. So I guess we do have to go into that whole thing. My original line current would have been easy. We take 750 kVA divided by our value of voltage. Our voltage is 600 volts. So take 750,000 divided by 600 volts would get us to that. Originally, this thing was at 1250 amps that I was going to be supplying to it. If I then go and solve for my far side of the triangle that I'm missing over here, this one, my watts, I'm going to be able to do that through Pythagoras, and that's going to go and give me a value of 559 kilowatts. Okay, that's all that they're going to do up this one, 559 kW. What do I know after power factor correction? I know that all of my source is only supplying kilowatts, and that the charged up cap is supplying the rest of that kVARs that are going to be part of this thing. So for me to now figure out what I have got for line current, my new line current, is simply going to be me taking that 559 kilowatts and dividing out my 600 volts that I have over here. Do that, 559 divided by 600 volts, and we come out to a value of 932. So we went from 1250 amps that we were supplying down to 932. That is a 300 amp difference that we're seeing over here. That's a pretty big deal, 300 and change. That frees up a lot of system capabilities, once again, for components to go and operate off of there. The last thing that they did ask, I think, as well, what was the last one? Let me just double check. Oh, power factor. What was my original power factor? To do your original power factor, just take your watts over top of your VA. 559 kilowatts over 750 kVA gets you to a 74% power factor. That's where we're going to leave off on this video. Just want you to go and take a look at that the paragraph that's right underneath your figure number 13. Figure number 13 shows the completed picture of what we just did inside of here. And then it has just a little bit of like words that are actually meaningful to us under there. It says that the basic unit of capacitance is going to be a farad or our microfarad, but that we're not going to go and sell power factor correction capacitors based on farads. They're always going to be sold based upon the kVARs of correction. And then they're going to go and have only two main ratings, the voltage and the kVARs. They're also going to have the frequency. We do need to know the frequency because we do know that that's going to go and change as well. And then underneath that, the last paragraph there talks about that they're going to come in standardized sizes. I am not going to go and find some of my kVARs like this, where I'm going to have 13.1 kVARs. Instead, I'm going to go and have jumps, steps that are going to be in between, where I'm going to be able to go and choose between like 10 kVAR and 15 kVAR. And I'm going to have to go and make an intelligent decision based upon which one of those would work best for my system over here. We're going to do that in the next set of videos, which is going to be partial power factor correction.